Okay guys, let's take a look at our lesson for today. This is Related Rates Day 2, and we're going to work through this particular problem. Just to kind of give you a heads up, on related rates there really are some categories of problems that we deal with. For example, there are the categories of like geometric figures like volume and that kind of thing, area, perimeter. I would say actually probably half of the problems, at least half the problems, have to do with that kind of thing, like some kind of a geometric formula. We also have problems that deal with trig. We're going to look at those kind of problems. We have problems that that's a whole category. This particular type that we're looking at today, where we're dealing with moving like cars or boats or trains, something like that, some kind of a situation where they're moving away from each other or moving towards each other, that kind of thing. That's the type that we're going to be looking at today. Really not possible to go over every type possible. I just try to go over big categories of related rates problems. So let's take a look at the one we have for today. So we have car A is traveling west at 15 miles per hour and car B is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads, and then I stop. Okay, I just want to do just like one or two sentences at a time. What I'm working on now is the setup of the problem. And in the setup of the problem, you're going to earn a point if you have all these parts of the setup. Typically, a related rates problem would be a free response problem. It's not going to be a multiple choice problem. So I would give you a point for the setup. So let's go through what would a setup look like. So we have car A traveling west. So we've got that kind of thing going on. That's car A. We have car B traveling north. So that's car B. This would be the intersection right here. Both are headed for the intersection of the two roads. Okay, so I'm good so far. Now it says, at what rate are the cars approaching each other when, and it gives us information. At what rate are the cars approaching each other? Okay, so before we get there, we're going to, first of all, approaching each other, what does that mean? The measurement is not these two roads. Approach it like the distance between them. How would I measure the distance between them? I wouldn't measure these straight line distances, right? I would measure here to get the distance between them, wouldn't I? I would measure from one car to the other, which would be a diagonal. So this would be the distance between them, and I'm just going to call that D. You just pick a letter, it doesn't really matter. So now let's look at the information that's given about the rates. It said car A is traveling west at 50 miles per hour. Now, so I have dA dt equals. They're giving me that number as speed. We really need to consider that number as velocity, not as speed. They're not going to tell us what the sign of the number is going to be. We have to figure it out. And for me, I'm a non-physicsy person, okay? I actually have never had a physics class. I have to think about it really in context. So what's going on? So cars are approaching a particular fixed point, this intersection. And the distance is increasing or decreasing between the car and the intersection. It's decreasing. All right, so we need to kind of focus on that. Problems are going to have a focal point. What's our focal point? They're headed towards the intersection. The distance is decreasing between them and the intersection. So that velocity is going to be negative. It's going to be a negative number because the distance is decreasing. Think about like a balloon. I think that yesterday we had a balloon example on the daily work. If the balloon is being blown up, the rate that volume is changing, is that going to be a positive or negative rate? It's going to be positive, right? Because the volume is getting bigger. And then if we look at a different situation, what if the volume is being deflated, the balloon, let's say it's being deflated, what would the sign of that rate be? It would be negative because the volume is decreasing. So we really need to pay attention to what the situation is, what the focal point is, and are we increasing or decreasing, because that's going to make a huge difference in your answer. Let's say, for instance, that we had a situation where one car was going away from the intersection and one car was going towards the intersection. That would be huge, right? The one going away would be positive, the one going towards would be negative. If we got those signs messed up, our whole answer would be wrong. You see what I'm saying? So we've got to pay attention to the sign of the rate, and we have to assign it. They're not going to tell us. So in this particular case, this distance between car A and the intersection, because the intersection is our focal point, right? We're headed to the intersection, is decreasing. The distance is decreasing, so it's going to be a negative 50 miles per hour. That we're given that in the equation. Then I have the rate dB dt, the rate that the car B is going. Again, it's going to have the same sign, right? Because the distance between it and the intersection are also decreasing. So that rate is going to be negative 60 miles per hour. Okay, so what else? So at what rate are the cars approaching each other? So they're approaching each other, I categorize as D, right? This. So dd dt equals question mark. There's always a when A is 0.3 miles and B is 0.4 miles. This is my setup. That's what you're going to get a point for, is the setup. What needs to be included in the setup? Well, a diagram labeling all of the values. That needs to be in the setup. The information that you've been giving in the problem needs to be written with the proper variables, like this right here, dA dt, dB dt, so forth. And lastly, it's the point in time we're interested in. What do they want to find? dd dt equals what? When? So you should have a question mark and a when in your statement right here, in our setup. So this setup is worth a point. Sometimes, I know you're probably going to find this hard to believe, but sometimes some students are only able to get the setup. They're not able to write the equation or work it out. You need at least a point, right? We need a point. So be sure that you set up the equation. Now, if you don't do the setup, you don't get the point, because I'm going to allocate a point towards setup. All right, so that's just the way it is. I mean, you can get the right answer, but if you don't do the setup, you're not going to get the full credit, right? Because you need that setup. Yes? The whole setup is 1 point altogether. So if you're missing any part of it, then you lose that point. Okay, because typically related rates problems on a quiz or a test are worth like 4 points. 1 point going to the setup, 1 point going to the equation, and so forth. So it's all or nothing. You either have it all there or you don't. So you get the point or you don't get the point. All right. So once we have the setup, if you remember the steps from yesterday, we get our setup, we see what's going on, we see the variables that we have to figure out what equation we're going to write to combine them, to relate them to each other. What kind of equation? Now I have a right triangle. It's certainly possible to do trig with a right triangle. Would a trig equation be an appropriate model for this particular thing? Not really. We don't have any angle measures, right? If we had angle measures, then we would go the trig route. But we don't have any angle measures, so that's really not going to help us. So, okay, we could do trig because it's a right triangle, but we're not going to because it's not going to help. So we need to think about other ways that we can relate those variables together. It's a right triangle, so we probably think Pythagorean theorem. That's an option. That looks like a pretty good option, actually, Pythagorean theorem. So let's go ahead and write an equation for Pythagorean theorem. So we would have b squared plus a squared equals d squared. Now I want to talk about this equation just for a moment and make sure that we don't do something that would just really ruin everything. I'm just going to lay it out there. Ruin everything. Okay. If you plug a number into our position equation right here before you take the derivative, you have just set that in stone and it's going to be wrong, right? If I plug, let's say I put a 0.4 and a 0.3 in here. Well, if I take the derivative of a constant, I'm just going to get 0, right? It's not going to be helpful. The only time you can ever, and you should write this down if you haven't written it already, the only time you can ever plug a number into the original equation is if that number will never change. Never. If the number will never change, then you're allowed to put it in the position right here. If it is going to change like this, are the cars always going to be 0.3 miles away from the intersection? No, it's just this particular time they are. They're moving, right? They're moving. Is the distance always going to be the same value? No, they're not always going to be the same value. I'm not allowed to plug in. That's one of the biggest mistakes that I see students make on related rates problems is they are eager to plug the numbers in, and then you just basically have lost everything, right? You can't that's not going to work. Okay, so just want to be sure that's clear. Never ever plug in a number in the position equation unless it won't change. Like the height of a cylinder. Is the actual height of the cylinder ever going to change? No. If there's liquid in it or something in it, that would change. We couldn't do that. But like something that's not going to change, that's what I mean. That kind of number we can plug in. All right, so now I have given that speech. I hope none of us in here will make that mistake. We're going to be great. So the next thing I need to be aware of is the number of variables that I'm using. Sometimes I have to find a way to get rid of a variable before I take the derivative, because I'm going to have to deal with tagging everything. Right? We're going to have to tag everything. I'm going to need a rate for B, a rate for A, and a rate for D. If I don't have ability to get all those rates, I need to be thinking ahead and deciding, well, what should I do to eliminate one of those variables? As we look at the information that we have, we see that we have a rate for A and B, so that's fine. And we want the rate for D, so there's really no reason to try to get rid of a variable. We're good where we are. So now we can take the derivative. So those are the things that you need to think about before you take the derivative. Number one, is there a number I can plug in excuse me, that will never change? And number two, is there a variable I need to get rid of? So here we go. Let's take the derivative. So we have 2b db dt plus 2a dA dt equals 2d dd dt. Okay. At this point, what I like to do is I like to just throw the numbers in there. Just throw them in. Because then I can figure out what I'm missing and what I need to look for. So here we go. Let's just throw the numbers in there. So B is 0.4. dB dt is -60. A is 0.3. dA dt is what? -50. 2. We were doing so well, weren't we? We got everything except the D. We need the D, right? We need that. So let's think about, can we find the D? We need to go back and look at the information and see if we can find it. We can, right? Because we're talking about this instant in time. So I'm just going to recreate that instant in time. So that's at 0.3, that's at 0.4. Looks like a 3, 4, 5 right triangle to me, right? So this would be 0.5. Okay, so great. That wasn't too bad. We went back and searched for the number that we're missing, and we found it. And that's perfect. So I have everything except the thing that I'm looking for. So let's do our arithmetic. Let's see. 2 times 0.3 times -50 is a -30. 2 times 0.4 let's see, 2 times so here we were 2 times 0.4 times -60 is a -48. I reversed it from my key. And then 2 times 0.3 times -50 is a -30. And then 2 times 1/2, well, that's 1. So dd dt. So we get, -78 is dd dt. So now let's put it in a sentence. All right, so the negative, that's a velocity number, right? We need to see what they asked us. They said, at what rate are the cars approaching each other? It didn't ask for speed, did it? It asked for a rate. At what rate are the cars approaching each other? Well, I could say, and really what I should say, is they're approaching each other. See, I'm giving them the words they gave me back. That's really how you should to frame your answer. You should use the words they use. Give them back to them. So approaching each other at 78 miles per hour. Now, because I said approaching each other, I don't need the negative, right? Because approaching each other means their distance is decreasing, so that rate is negative. It would be like when we were dealing with temperature. Remember when we said that if the rate of the temperature was changing was -2 degrees, what did we say? We said either the temperature is changing at -2 degrees per minute or it's decreasing at 2 degrees per minute, right? We don't do both. So I'm not using the negative, and instead I'm using approaching each other, and that's just fine. All right, so our next related rates problem, how are we doing on it? We okay? Okay.